Hello everyone, and welcome back. Last time we started looking at work and kinetic energy. We're going to continue with those ideas today, and we're going to look at work and the conservation of energy, not just the conservation of mechanical energy, but a much more general conservation of energy. Last time we developed this definition of work, if you'll remember, going from some point one, an initial point 1 to a final point 2, we can determine the amount of work done by a force acting on the object. As we move the object from point 1 to point 2, we integrate F dot dr, the force that's acting on the object dotted into the infinitesimal displacement vector. We take that dot product, we integrate that from point 1 to point 2, and that is the work done by the force, whatever this external force is. We looked at a couple like gravity and the spring force, and we determined the work in those cases. What we found out was that, in particular, like for those cases, we were able to define a potential energy that went along with those forces. What I'd like to start with is to try and understand when can we actually define a potential energy? For what kinds of forces can we define a potential energy, and how do we go about doing that? Well, let's use our example of gravity that we did last time to try and figure out what were the necessary conditions for that. If we'll remember, we looked at a skier going down a hillside, and let's imagine that the skier starts at some initial height, we'll call it h1, and ends up at some final height, h2. And the important thing that we figured out was that it didn't matter what the shape of the hillside was. All that mattered in determining the work done was the initial height and the final height. And what we were able to do then was to define a potential energy, a gravitational potential energy, that was mgy, that only depended on the height of the object. The skier started off with a potential energy, a gravitational potential energy of mg h1, h1 being the initial height, ended up with a potential energy of, let's say, mg h2. We actually had the skier go down to zero height in the problem. But what is that zero height? What does that mean exactly? That's the place where the potential would be zero. So in this case, our y equals 0 height is the place where the potential equals 0. And that actually turned out to be an arbitrary point. We could choose our y origin to be anywhere we want. We could choose it to be ground level, but I mean, what is ground level? Does that mean sea level, or whatever the height of the ground happens to be where you are? Does it mean the level of the floor? If we were upstairs, is it the level of the floor up there? Well, it's arbitrary. For whatever problem we want to choose, we can determine, or we can choose our zero height to be wherever we want. But once you determine it, once you choose a height, you have to keep that throughout the problem. You can't just change your arbitrary ground level. You can't change that in the middle of the problem. Once you choose it, you have to stay with it, or else your values will change, something like that. Okay, so when can we do that? What kind of forces will allow us to do that? Well, what's the important point here? The important point is that all that it matters is what was our initial height, what's our final height. The way we got there didn't matter. That's the important part. The way you go from one point to another does not affect what basically the amount of work done is. If the work does not depend on how you go from point 1 to point 2, if it is path independent, that will allow us to define a potential energy. Let's see what that means. Let's imagine that we have some general force, and we want to calculate what the work done is to go from point 1 to point 2, and it is then the integral from 1 to 2 of f dot dr. In other words, we're going from some point 1, ending up at some point 2, we're going along some path like that. And the path doesn't matter. Well, now let's think about this. What if we were to go from point 2 to point 1? So what would be the work done in going from point 2 to point 1? It would be the integral from 2 to 1 of f dot dr. r. Now, how would that relate to this quantity here? Well, let's imagine that we were to just go along the same path, but in the reverse direction. So all we would be doing, basically, would be changing the direction of dr. We would integrate f dot negative dr, coming back the other way. Well, if we take the dot product between a vector and a negative vector, what do we get? Well, let's just take a look at that just for a second. You might guess what you'll get, but let's look at it mathematically and make sure. Let's imagine we're going to take a dot product of a dot b. And we have some vector a. Here's vector a. And let's say here's vector b. And there is some angle between them, theta. And we take the dot product and we get a, b, cos theta. Well, what is going to be a dot negative b? What will we get if we take the dot product between a and the negative of the vector? Well, where is negative b? Negative b is pointing in the opposite direction, but with the same magnitude. So that would be negative b. What if we take the dot product between a and negative b? Well, that's going to give us the magnitude of the first vector, a, times the magnitude of the second vector, but the magnitude of an opposite vector is the same as the magnitude of the original vector. That was one of the things we determined about vectors. The negative of vector is a vector that points in the opposite direction, but with the same magnitude. So the magnitude of negative b is still b. And then times the cosine of the angle between them, which will be this angle. So here's a and negative b. We want this angle, which is what? Well, that's just 180 degrees minus our original angle, minus theta. So this is 180 minus theta. Well, what is cosine of 180 minus theta? Do you remember that trig identity? If you don't remember those, and to tell you the truth, I have trouble remembering them, but I do remember what sine and cosine look like. Let's just remember, what does cosine look like? Cosine starts at 1, goes down, and comes up like that. So this is at 0 degrees, this is at 360 degrees. I typically remember them in terms of degrees, but you can also remember them in terms of radians. 0, 2 pi, pi in the middle. So this is 180 degrees. So if we come over here, some angle theta, or 180 minus theta, how does that value compare to that value? Well, they're just exactly negatives of each other. So cosine of 180 minus theta is negative cosine theta. So this is going to be negative a, b, cos theta, which we see is exactly just the negative of a dot b, which is what we might have guessed. So a dot negative b is negative a dot b. We can pull that negative sign right out to the front. That might not be too much of a surprise, but I want him to make sure that that's actually the case. So what does this tell us? Well, rather than going from point 1 to point 2, if we go from point 2 to point 1, we're going to have the same force, but we're going to have our drs in the opposite direction. In other words, going from point 1 to point 2, we'll have drs pointing in this direction. But if we go from point 2 to point 1, we'll have our drs going in this direction. Well, what's that going to be? It's just going to be the negative of the integral from point 1 to point 2. So this is just the negative of the integral from point 1 to point 2 of f dot dr. So what would be the sum if we took the integral from point 1 to point 2 of f dot dr, and then we added the integral from point 2 to point 1 of f dot dr? What do we get? Well, the integral from 1 to 2 and from 2 to 1, but 2 to 1 is just the negative of the integral of 1 to 2. So we've got the integral from 1 to 2 minus the integral of 1 to 2. Well, that's just going to be 0. Well, what is this telling us? This is a very interesting result. Let me get rid of this middle part in here. What is this telling us? Remember, it doesn't matter the path that we take from point 1 to point 2. So if we integrate from 1 to 2 along some path, and then we go from 2 to 1 along some path, but we could choose a different path because the path doesn't matter, it's only the beginning and end point. So to go from 2 to 1, let me change, I don't want us to think that we're going in that direction. Let me put the original directions back on there. Okay, we're going this way, from 1 to 2, but then we go from 2 to 1 along some other path. What is this telling us? That if we start at 1 and end up back at 1, we end up having done 0 work. We can write this in another way. We write this as an integral of f dot dr, and we put a circle around the integral sign. This means it's a closed path or a closed loop. So wherever we start, we go around and we come back there, we end up with that result being 0. When that is true, when the force that we have around any closed loop, if we integrate the work done by that force around any closed loop, if that is 0, we call that force a conservative force. Why conservative? Well, because we will actually be able to define a potential energy so that the energy is conserved. We'll come back to that. All right, very, very good. Now, how does this work with gravity? Well, let's just think about the work done by gravity. Here we go. As an object moves downward, gravity does a positive amount of work on it. So as the object comes down, gravity does work on it. It's decreasing its potential energy. That energy is going into the kinetic energy, and the kinetic energy increases. But if the ball were going upwards, gravity is doing negative work in that case and removes exactly the same amount of kinetic energy as it put in on the way down. So the amount of work that gravity does going down is exactly opposite the amount of work that gravity would do going up. And so the net work done around a closed path by gravity is 0. It's exactly the same coming down as it is, it's opposite, exactly opposite, coming down what it is going up. So that's an example of this result, that it doesn't matter going down the ski slope and then going back up. The amount of work that gravity does going down the ski slope would be exactly the same as the amount of work getting that person back up to their original height. All right, very, very good. So how can we go about defining a potential energy? If we have a conservative force, one whose path integral around any closed loop is 0, how do we go about defining a potential energy for that force? Well, all we have to do is take one more step.